right, welcome back everyone to the second day of Complexity Weekend. We hope you had a lot of fun yesterday. We had a lot of great talks. We all got to know each other in Keybase, and we really started to wrap our heads around this concept of complexity and starting to kind of form an idea for what this approach to science is all about. So I just wanted to jump right into it today and actually just dive into this question: what is complexity? That's something I got a lot of great feedback from people on yesterday, where we were circulating a lot of interesting ideas around complexity, but nobody was really, a lot of people were saying, I just want to know the definition of what it is. I want to come to some understanding. If I go to a conference called Complexity Weekend, can somebody tell me what complexity is? And it's kind of a hard thing to do. And so we decided to kick the can to you and have you try to do it. For each other, because it really is something you have to unpack with the particular problem you're working on or system that you're dealing with. And so what I want to really kind of do as an icebreaker today is actually have us jump into the program together. I'm going to wait a couple of minutes while people start populating something that we've set up in the program for you right here. So here's the program you should be able to see on my screen. And this has things like the conference schedule, the facilitator info, all the information about our great facilitators for the conference, including their Keybase usernames. You can reach out to them directly. And the activity we're going to do right now, which is to jump into the participants tab of the program. The program will be linked into Keybase. If you look in Keybase right now, if you have no idea where I'm at right now, but if you go into this participants tab of the program, you can see there's a column here called Complexity Is. And that's an opportunity for you to process all the talks you listened to yesterday, the conversations you had yesterday, and really start to come to your own understanding of what complexity means in systems, what complex system behavior looks like or is like in the systems that interest you most. And we'd really like to just take some time here to populate some of these fields in this column. I'll give you some time, maybe 30 seconds or a minute. Start seeing some activity here. And you can always come back here and edit your answer if it is your conception of complexity changes over the weekend. So some great ones people already put. Some is more than the behavior of the system is more than the sum of its parts. Kind of a classic complexity phrase. What's another one? Emergent patterns and networks was a great one. Let's see. There was one I really liked I saw yesterday. It's basically saying complexity is what makes life interesting. I thought that was a pretty cool one. Systems level order arising from individual level rules. That was a great contribution. So go ahead and hop in here, add your definition of what you think complexity is, and we will all come to some sort of emergent understanding of this terminology in our wonderful complex adaptive system that is our conference cohort. All right. So you can definitely bookmark the program because this has all the information for the conference. You're going to be referring to it again and again and again. And I want to just kind of go over the goals for the weekend hackathon. We talked about these yesterday. I'm going to be rehashing some content, but some people are going to be new this day. And also it's good just to go over this stuff again and again. So the goals for our weekend hackathon were really to learn complexity science by doing. We have a philosophy at this conference that's basically, in order to really understand complexity, you really have to get your hands dirty, working in a complex system, trying to understand how to change the behavior of the system, how to unpack that complexity term in the particular system that you are working with. Everyone finds a team. So no matter what your background, your perspective, there's a valued place for you in a team. To contribute to this many complex problems that are out there today, but in particular, the COVID pandemic that we're working with right now for this particular complexity weekend. And working with people on projects you'll want to continue. So this is really a community of practice that we're all trying to build together. So you can start a project with the team this weekend, but really the goal is to stay connected and work on projects together in general. So if you don't even continue the project you have to do this weekend, that's totally fine. Just stay connected with everyone. We're all amazing doers and complexity thinkers now, and we can stay together on each other's projects and really just create this wonderful community of practice. So I want to encourage you all to come up with your own personal goal for the weekend and post it into general. And also, if you're new, welcome. And please post introductions and let everyone know who you are, why you're here. So just really quickly to rehash the conference technology. We're using Keybase as kind of the back end for the entire conference. And if you were here yesterday, you probably saw a ton of activity. There's a lot of great chatting going on, a lot of great conversations, amazing references being thrown around. And so a key tip for Keybase once you're in is really to go to the Keybase team name, complexweekend.May 2020, click the gear next to it, and click Browse All Channels. That's how you see all the different threads that we're talking in. And there's a kind of a format to the threads. You'll see some key ones I'll go into, like I need a team, ask the facilitators. I'll go into those in a second. But really, these explore channels are the ones where you're going to find your teams today. This has all the great content and topical channels where you can talk about economics and all the different aspects of complexity and economics. And be sure to post in general during the live streams. That's really where our chatter is. You can post in the YouTube comments, but we're not reading that so much. It's in the general. And pretty much join as many channels as you find interesting. Find your team today. There's a whole process for it. We'll lay it out. And really post a request if you have any other Explore channels that you'd like to see created. We're going to be using Jitsi a lot more today. Some people used it yesterday a bit in the breakouts. It's our video conferencing tool. It's really easy to use. The main tip I want to use, you really just got to click the URL to go into it. That's all there really is to it. But a great tip is to actually, if you either go to gallery view and double click your video and rename yourself there, or if you do the ... in the bottom right corner, go to settings and the profile tab, you can change your display name. And the way that we've been linking Keybase to Jitsi and to Online Town, which I'll share in a minute, is you put your first name and then parentheses, you put your Keybase username. So that's a great way just to link the two so people know who they're talking to and how they can message you in Keybase and hopefully start a team with you. Online Town, if you got to experience it yesterday, was a fun, chaotic mess, and I loved it. It was basically our virtual water cooler. You can go in, you're this cute little avatar, you can walk around, and you can talk to people nearby you in a video chat. So you can go off and go down to the, I don't know if anyone went down to the ocean at the bottom. It's really fun. Go all the way down to the ocean in the map. You can sit on the beach, talk to the group of people about what you just learned. So that's a lot of fun. It's open 24/7. So literally in the middle of the night, if you're just like, I want to see if anyone's in it, hop in. This is the URL here. You can bookmark that. And be sure to change your display name to your first name and in parentheses, your Keybase username. So the Keybase channels themselves are going to be split into kind of essential ones for the conference that you should definitely be in to not miss anything conference proceedings wise. And then also these explore channels, which I went into, right? The topical channels to help you find your potential teammates. And there's going to be facilitators in those explore channels really helping with team formations today. We'll get into that. Introductions, jump in there and say hi to everyone. That's kind of a great start to the whole Keybase experience. General, again, is our live stream chatter. Tech support is actually resolving any issues with Keybase, Jitsi, Online Town, any technology your team starts using. Pop it in there. We'll try to answer it as soon as we can. Ask the facilitators is a way to ask our 21 great facilitators all at once something, and they'll just hop on it, and we'll find some resolution. Request is where you can ask the conference for anything you might need, especially new explore channels. That's really what I want to articulate is let's expand that to the full topical set of what we're interested in as a cohort so that we can form the best teams. And I need a team we'll be using today. This is the catch-all channel to go if you want to accelerate the process of finding a team. So if you're finding that it's a little bit slower than you thought to really find the people you're connecting with, hop in there, make a post, and we'll make some magic happen. And lastly, random is for all those juicy memes. Pop them right in there. Any miscellaneous papers, references, anything like that would be awesome. So I'm going to go ahead and pass it off to our co-organizer, JP. JP, you want to pick up and share with everyone?
Sure. Yes. And here. So the goal for today is team formation, and this is kind of auto-generative process that you'll be forming teams based on your interest categories and what you're really interested and passionate about. From yesterday, we have a lot of people coming in from very diverse backgrounds, weighted towards academia and students, but there's also business professionals, people in government, people in health. So keep that in mind. We'll be working with our facilitators today, and this is an amazing team of people from around the world, 21 experts in their own fields. You can find their details in the schedule in the program, and they are here to guide your, not guide, but assist your thought process and assist in anything you have from forming teams to technical questions. So let's say you have a team coming together who wants to look at a COVID data set and pull out, pull out patterns from it. We've got somebody for that. So split up based on your interests, and we will get to it thusly. And mostly, don't be afraid to contact them one-on-one. They are here for you. So that's the essential component of this. Again, some simple rules. Don't be afraid to participate. If you find yourself being quiet, ask for the mic. Don't be afraid to let people know what's needed. Also, another key: speak to stakeholders. So if there's if you're getting onto a route where nobody's an expert, but you all have good technical skills, bring somebody else on board. So we'll be splitting into groups today. So Jitsi chats. This is our in-person getting to know each other. So keep your video on. Get people knowing who your Keybase username is by putting it in the chat. The key here is all about mixing. All right. So to this effect, and this is our operative part, you've been assigned to a group A through F, and this is all in the program schedule. So click on the participants tab in the program schedule. And what we'll be doing is we'll be going through 6 30-minute workshops where a facilitator will come to you to give a talk on a competency. All right, they'll be rotating in, and you'll kind of have your home room. So this will be a bit of a cohort. All right. So one operative thing to do from now: start private messaging with a team seed in those interest groups. So in the Explore channels, see if you can start kind of nucleating some common interests with everyone. And I think from there, I pass on to Dan to keep our schedule. So thank you, Dan.
Greetings, JP, and everyone. Hi, thanks so much for joining us on Saturday. We're really looking forward to these first 2 talks by Justine and Will before we jump into the sessions. So I'd like to introduce Justine Schott. She's an expert in education technology and data science. She is a data analytics manager at Education Superhighway and a data ambassador at DataKind SF. So thanks so much for your talk, Justine. We're really looking forward to it.
Hi, thanks for that intro. Let me just share my screen. I hope everyone has their coffee or tea early in the morning. Thanks for joining so early. Can everyone see my screen?
We can see your screen. You might want to go full screen with the presentation, and then if you hit the camera again to enable picture-in-picture in the bottom right.
Great.
Perfect.
All right. I will leave it like this because I'm going to be alternating between my presentation and browser, so apologies for the big border there. But this should be quick. So just a little bit about me. Thanks for that intro already. In case you haven't heard of DataKind or Education Superhighway, DataKind's goal is to partner experienced data scientists interested in pro bono work with nonprofits that don't have data scientists at their disposal. So the most recent project that I completed is a probabilistic record linkage model with an NGO called Muso. And if you haven't heard of Muso, they work with community health workers in Mali. Really great organization. And I also work at Education Superhighway. And Education Superhighway is a nonprofit whose organization, it's a nonprofit organization whose mission is to get high-speed internet to all of America's public schools. So I also wanted to mention that I actually moved to the field of education through Education Pioneers, an organization that advances professionals to increase the talent supply for key educational organizations. And I also started my career as an actuary. So if you happen to have any of those things in common with me, I'd love if you could reach out and we can chat about it. But today I am here to talk about data. So we have a document linked in the Explore Data ML Keybase channel, Complexity Weekend 2020 Datasets. If you're already in that channel, you may have clicked in and seen it. But I just wanted to say that I am excited to be doing this first thing in the morning because data is kind of like a chicken and egg thing. You want to look into the data to get ideas, but if you get certain ideas, you want to look for the data. So here I am to show you some data sets that may get you excited about something, but you may want to also check in with me later if you want to take a different route later on throughout the day. So I'll be available all weekend, and I'll let you know how you can contact me after this. So let me just go to the spreadsheet. This is the spreadsheet. Like I said, it's linked in the Explore Data ML channel, so feel free to check it out. I'll just show you a few different features of this list. So we have the title, a small description, some tags that you can filter by. So if you're interested in health, resources, education, we have a few tags. Type is very important. There's a couple types: model, dashboard, and data. Anything that's data is actually like data that you can build something off of in its rawest form, mostly CSVs. A dashboard is something that can kind of help you explore more. You can click through it, kind of build some assumptions and less intense models out of dashboards. And then a model actually may not have data at all. It may be a model for helping you in your analysis, totally separate from data. So those are the three types that we have here. I believe there's also a fourth type, which is insights. So insights is really just like some article, an organization didn't publish their data, but they have a lot of great metrics in an article. So that's what we have. And then we also have the scope. So globally, nationally, by country, things like that. And most importantly, Source Connect. So we have so many great facilitators here this weekend, and a lot of them own these data sets. So this is something that I wanted to share. The Source Connect may not be the owner. For example, I am not the owner of COVID Act Now, but I do have a personal connection to this data set. So hopefully if there's a specific question that we can't answer in this weekend, I can reach out to that person. And there's a few other situations where that's the case with our source as well. And of course, the link, most importantly. One other thing that I wanted to mention is we have a facilitator that has a database with a lot of these data sets already in it. So if you're an advanced data user and want to pull data from a database already, there is a way to access some of these data sets from a database. So feel free to reach out to that facilitator. I believe he's already put instructions in the data ML channel as well. So just FYI there. Great, so let's talk about some of these data sets. I want to start out with seeing how many people are familiar with these data sets. I'm going to scroll all the way to the bottom to this visualizing Johns Hopkins data. So I'm going to put this name into the general channel on Keybase, and I want people to emoji it with a thumbs up or a green check mark if they have heard of this data set before. I'm starting out with this data set because it is one of the more commonly used data sets. And I think from here this is one of the most commonly used one, and then there will be more niche and specific ones after this one. So I'll click into it here. This is the GitHub link. You may have seen this GitHub link as well. And from here, there is a dashboard that you may have also seen, which I'll click into as well. Oh, thanks for the link. Didn't realize the spreadsheet was blurry. But yeah, this is a dashboard that maybe a lot of you have seen, and we have the data that powers this dashboard. So give an emoji if you've seen it before. If not, that's totally fine. But yeah, it looks like we're getting a few emojis. So great. Maybe some of you haven't seen this data set before. Awesome. So let me give a little bit of information about it. So this data set is really one of the most well-respected data sets for collecting statistics around COVID-19. So a lot of data sources are put into this from World Health Organization, from specific governments all over the world. So it's basically a really well-respected one-stop shop for a lot of statistics. Really basic statistics like how many cases are there, how many deaths have there been, who's recovered, basically anything that you may have seen in this dashboard before. So the way that you can access this data is pretty straightforward. If you want, there are two different links, but this is really the specific data set. If you go into, for example, daily reports for the US, you can click in and download any of the reports for any day. You can see it's just a CSV, so you just click it, download it, use it however you like. And then there's also a time series data set as well that combines all of the days into one. So US, global, confirmed deaths, etc. So this is a really great source that I think a lot of organizations are using as kind of a baseline. Also, what's great is because this data set is so popular, there are a lot of visualizations and tools that have been used, that have been built off of this. So that is the subsection here, any data, dashboard, or tool that has been built from this. So for example, the Associated Press created a dashboard from this data, combining a few other data sources. I'll just click into this one, but feel free to click into these others as well. They have some really great insights and interesting visualizations. So data.world is a really interesting website. I'll just talk about this while it's loading. They have a tool that allows you to visualize data, not just download it. So you can see here, you can view this data or just download it directly from this website. You can also click explore this data set. Like I said, they have a tool that you can use. So if you want to just look at the data here, that's something that you can do. You can query off of it using this tool. And this is a free tool for whoever wants to use it. So this is kind of being slow, but feel free to ask me any questions if this seems like something that you'd be interested in using. I did want to go back to the dashboard that the Associated Press made because it's pretty cool. So another thing that I'll mention is that this other section up here is titled Collections of Resources. So a lot of our great facilitators have created these collections that feed into their tools. So I won't go into those because I'm sure they will tell you all about their contribution and the data that they used. But just FYI, throughout the weekend, if you hear a talk and you want to know the data behind it or see the data behind it, those are also linked here. So one of these collections of resources is the data.world coronavirus resources. So that's why I'm linking you to this right now. They have a ton of different dashboards and data sets in addition to the ones that I've already listed in this resource. So this is kind of the, we have a lot of really specific data sets. If you want to learn even more, go to these even more collections of resources and feel free to contact these facilitators to learn more. Sorry that it's blurry. Let me see if I can do a little zoom out or zoom in to fix the blurriness. Hopefully that's a little bit better.
And also on the three bottoms, on the bottom right of your Jitsi, manage video quality. Just make sure that you're in high definition.
I am, unfortunately. So I'll try to spend a little less time on the spreadsheet. Feel free to click into it at your leisure, but I'll try to just explain these resources that are listed here, because hopefully that is a little bit less blurry. Great. So this Associated Press data set, they have so much information about what they've added here. So what's really great about this data set is they've taken the statistics like deaths, testing, cases, and they've added population. So that's like a really interesting addition because then you can see, per capita what's been happening. Here is their dashboard down here. So you may have seen this, this one here. So you can see by county confirmed cases. And I believe if you click into this link more, you'll see more options for seeing. So here, let's look at the Bay Area since that's where this is located, our weekend. Santa Clara County, you can see the cases per 100,000, deaths per 100,000. So this data is all available from this specific data download if you didn't want to take the time to be joining data sets. What's really great is a lot of these resources have already done the hard work. So before you start taking raw data, joining things together, try to look through this, see if it's been done already, because a lot of really great things have already been done. feel free to ask me, and I can try to direct you to the right place as well. So that's what I'm going to be talking about for the Johns Hopkins data and visualizations. Feel free to keep clicking. There's a lot of great visualizations happening here. I'm going to go back to the top here and talk about some more niche data sets. I'm not going to talk about the ones that other facilitators are owning per se, because I'm pretty sure they'll be going into that in a lot more detail in their talk. So I'll start with the COVID Act Now data set. This organization is putting together kind of like a report card or like a warning system for the US. Is your state ready to open is basically what's happening. And they have a lot of different indicators for doing that. So I think this is a really great resource depending on what you're doing. If it's related to opening or businesses, this can be a really good check to see if you're on the right track. If you're making similar kind of recommendations to what we're seeing in this dashboard, that could be great. So if you look at California, for example, you can see that we have medium infection rate, so active cases are slowly increasing. So we want to have this number at around 1. The positive test rates is not in the right range, unfortunately. What is great, as I'm sure you all know, is we have a lot of ICU headroom, and the contact trace is still at medium. So this is a really great dashboard. I was really comforted and surprised to see that there are a few states ready to open. But yeah, that's a really interesting project that's been happening as well. Cool. So the next one that I'll go into, I don't want to talk about all of these, but I think a really great one is looking for the Google mobility reports. So Google, obviously, we all use Google Maps, and Google is able to track how our phones have been moving. So they have mobility reports to kind of track how people were moving around before COVID restrictions and after COVID restrictions to see if people are actually following these guidelines. So again, you can just download a CSV, pretty straightforward. If you want to check it out. They also have reports, so you can see by your area how certain types of locations have increased or decreased mobility to them, which is really interesting. So I'll also check out Alameda County. That's where I am specifically. Oh, it looks like you have to download as a PDF. So you can see a lot of decreases in retail and recreation, grocery, a slight decrease, decrease in parks, transit stations, workplaces, and residential increasing, which kind of makes sense. It means people are spending time at residences instead of outdoors, which isn't ideal. We're supposed to be sheltering in place, but yeah, just interesting reports there. So all of that data is available to download as a CSV. The next one I wanted to talk about is SafeCast. This is an organization that's been working with DataKind. So I have contacts with them if anyone has any questions about this data set, so I'll go into it into a little more detail. SafeCast is basically making a map of testing experiences. So people can self-report when they go and try to get tested and what the result was. So let's look at this in the middle of the country. Someone went with symptoms of COVID-19, and they were told to go home and to go to the emergency room if their fever got worse. So you can see they indicated this with an orange indicator, not ideal. They did not get tested. A green indicator, however, it looks like there's a lot of detail, like if people were wearing masks and things, but if you look into this even more, you'll see that green means that they were able to get tested at this specific hospital. So this is a really interesting and global data set. It's not very large, it's all self-reported. So I think last time I checked, there was like a few hundred incidences, but still an interesting data set to explore. So the reason I'm going into this may not be interesting for your project, but there are just so many data sets out there for specific use cases such as this, and some things that you may not even realize. And I'll try to go in as many as I can in this amount of time, but I am getting to the end. So I wanted to lastly talk about this data set, which is actually created by Education Superhighway where I work. We've pivoted, like I said before, we want to get high-speed internet to America's public schools, but we have pivoted to try to make informational metrics and things for students at home. So we want to make sure students can keep learning when their schools are closed. So we've estimated that 9 million students don't have reliable internet connectivity at home, and we actually created an interactive map. Looks like I don't see the map right now, but I'll reach out to my contacts and see what's going on there. But basically, it shows by state how many students don't have reliable internet at home. So this is a really great resource. And it also talks about how we get to that estimate. And I believe I might be out of time. I might have time for one more. Feel free to cut me off.
Show one more and we'll bring the next speaker on. Thank you.
Great. So Digital Wish is another organization that we've supported. Digital Wish did their own survey for surveying how many students are unconnected, how many students need devices at home, how many students need internet. So you can see 10.6 million students don't have at-home connectivity and 11.8 million students don't have computers. 10.8 is obviously different from 9, but we had different methodologies for getting there where they used a survey and we used a model. So it's interesting to see that it's in range, but there are obviously some differences. But yeah, if you wanted to use these numbers for anything as inputs into your model, for example, you wanted to know how many students are being left behind to kind of project what could happen to these students in the future, that could be something that you want to do. So yeah, if you have any questions about any of these resources, obviously there are a ton of resources and we don't have time to go over all of them right now, but basically what I wanted to say is I'm here to help. I'm here to help you figure out how to get this data, how to use it. So reach out to me if you need support or if you want to contribute some data sets. Here's my Keybase name. Here are my office hours, but I'm really happy to talk at any time and help however I can. So thanks.
Thank you, Justine. You can leave the Jitsi. So our next speaker today is going to be Professor Will Hamilton. He is an assistant professor of computer science at McGill University in Canada. He's an expert in machine learning, network analysis, and natural language processing. And after hearing that awesome talk by Justine about what kinds of data are out there, as well as things that posted about in general, Will, I would love to hear about what we can actually do with data.
Yes, thank you, Daniel. And let me just get my screen shared. So, and hopefully my bandwidth stays okay throughout the talk, but let me know if anything arises. Okay, can you see?
Looks great. And if you want to re-enable the picture-in-picture on the bottom right, but it looks great. Thanks, Will.
So, and now you can see me as well.
Looks good. Go for it.
Awesome. Okay, great. So thank you very much for the introduction, Daniel. Today, given it's a relatively short talk, I'm going to focus on a particular type of methodology that we can use for analyzing data related to COVID-19. And this is focusing on what we can do with what I'll call graph methods, but also might be familiar to many of you as network analysis methods. And why I use the term graph will maybe become a bit more clear in the coming slides. So why are graph or network analysis methods particularly useful for COVID? Well, obviously, given all the data sets that have been previously discussed, you might notice that a ton of these have a network or graph structured nature. So for example, grouping things into 3 big buckets. One of the most important data sources we have is obviously biomedical treatment data. A lot of it can be represented as what we call knowledge graphs or as multi-omic interaction networks, things like the interactome. There's obviously also a lot of epidemiological network data. And then lastly, a really interesting and perhaps understudied in a lot of the work that's been coming out on COVID is the role of supply chain. And so here again, we can really think of the supply chain for the supply of looking at, say, necessary goods for medical workers or even just masks for the general population, so on and so forth, even food. There's been a number of issues relating to supply chain. And a lot of these sorts of supply chain problems really can be represented from a graph or from a network perspective. So I'm taking here quite a general view of what I mean by a graph or a network structured data set. So talking about data sets where we're interested in not just a set of entities, but also the relationships between these entities. So again, what's key and what's shared between all of these different applications or data sets is that they involve heterogeneous data, and they also involve relational or network structures. So the type of technique I'm going to be focusing on today and giving only a very high-level introduction to and talking about some of the concrete ways we can use this methodology is a technique that's broadly called graph neural networks or graph representation learning. So to keep things very high level, and I'll provide a pointer to some more detailed notes on this, the goal in graph representation learning or using graph neural networks is that we want to do machine learning on graph structured data. And the way that we often look at this is we're trying to learn some representations for all the nodes or the entities within this data. So here what I'm showing is an example input graph. Our goal is to learn some representation on a node, say this target node A in this graph, so that we can make predictions about this node. So if this is an epidemiological network, we might want to predict risk of infection. If this is a biomedical interaction network or knowledge graph, we might have nodes representing drugs and maybe nodes representing diseases, and we're trying to predict interactions between these. And the way we do this is by applying neural networks that operate directly on the graph structure. So this cartoon visualization here that I'll expand on in terms of some actual equations summarizes the idea that in order to generate a representation of node A, this is going to be a neural network that takes information that's being passed, we call them vector messages, from all of A's neighbors, nodes here B, C, and D. And then in turn, this information that nodes B, C, and D are sending to A then depends on information that they're aggregating from their neighborhoods, and so on. And so to give a bit more formal mathematical detail for how this works, again, keeping this as more of a quick overview that I'll then provide pointers for more detail on. The idea here is that we're going to initialize some representations for all of the nodes or entities in our graph or network. So we call these the layer 0 embeddings. And we're going to initialize these to just whatever information we have. So if we have a biomedical interaction network where we have proteins, maybe we have some features, some information about the proteins, and we're going to initialize some vector, some feature representation for each node based on this information that we have on hand. Then we iterate what we call a number of steps of message passing, where the kth layer embedding, so the representation of a node U at the kth layer of this graph neural network, is going to be some nonlinear function of information that this node is aggregating from its neighbors. So here we're taking the sum of all of the representations of the node's neighbors in this graph, and then we're combining this with the information that we had about this node from the previous layer, where we're doing this using linear transformation matrices. I've denoted here W self and W neighbor, and we also have a bias term. And so for those of you who have a background in machine learning or deep learning, this looks a lot like a multi-layer perceptron, a standard neural network. It also looks somewhat like a recurrent neural network, and it is very closely related to these things. This is the basic graph neural net, and the key difference is that whereas in a basic feed-forward neural network, information is just flowing from hidden layer to hidden layer in an unstructured way. And in a recurrent neural network, information is flowing across a chain or a sequence, usually a time sequence. In a graph neural network, information is flowing according to an arbitrary graph structure. And in general, this is just the basic graph neural net I've shown here. In general, people build all kinds of graph neural nets where, again, we're going to learn these updated node representations at each layer that depend on some general aggregation of the information in the node's neighborhood and some general update function that combines this aggregated neighborhood information with the previous layer representation of this node. So people implement these aggregate and update operators using sums, using LSTMs, using all kinds of deep learning techniques that you might imagine. And here, just to pause for a second, part of the reason why I'll refer to these data sets as graph structured data sets as opposed to network data sets, which would be quite common, especially in the complexity literature, is because there's a bit of a terminological clash with neural network and networks. So I generally will refer to graphs as the data and then neural networks as the method, but it is difficult because these terminologies overlap and clash all over the place. And I provided a link here to some notes. It's actually a short book on graph representation learning that elaborates on all of these techniques as well as the historical beginnings of these techniques in spectral graph theory and graph signal processing in a lot more detail. Okay, so with that very quick high-level introduction of this general technique of graph neural networks, I'm now going to discuss some possible applications. I have maybe a mild bias here about why I'm focusing on these kinds of methodologies, because my lab at McGill, as well as a number of collaborators, are actively working on computational drug design, computational treatment design using graph neural nets. So that's where I'm going to spend most of my time. The last 3 applications of epidemiological forecasting, demand forecasting, outbreak tracking and tracing, which are also things you can do with these kinds of techniques, I'm likely not going to get to in detail. And I also want to raise, even at the beginning, a point of caution here, which is that a lot of these applications, especially tracking and tracing and epidemiological forecasting, have really big fairness, privacy, and other issues. So this is, of course, is also an issue in drug design and treatment design, but when it comes to trying to do especially outbreak tracking and tracing, which you could do using the techniques I'll talk about today, I do believe there's maybe too many societal risks to try to dive into that without a lot of forethought. Okay, so talking about now the task of computational drug design. So the goal here is that we want to try to generate or learn a new molecule structure, so a de novo molecule design that could act as an effective antiviral agent, also potentially could act as something to help out with the immune or other aspects of the biological response to COVID-19. And really here, there's 2 subproblems. One is, how do we represent molecules and predict the properties of molecules? So how can we represent a molecule in such a way that we can effectively predict whether or not it's going to treat something, whether or not it's going to interact with a particular protein, and so on? The second subproblem is actually then generating molecules and figuring out how do we search over the absolutely giant space of possible small molecules and figure out which ones might be useful as a treatment for, say, COVID-19. So the way that we represent molecules, unsurprisingly, the current state of the art in this space, I wouldn't be mentioning it if it wasn't using graph neural networks. So there is other techniques, very good techniques coming from chemistry. And right now, graph neural networks are just starting to be the kind of dominant paradigm for up-to-date state-of-the-art applications. And generally, the way that these techniques work is that we're going to represent a molecule as a graph. So every atom is a node, the bonds correspond to edges, and then we run this graph neural network, this message passing idea that I introduced earlier on these molecule graph structures. We get representations for all of the nodes. We then aggregate these representations together, and then we can predict different properties of the molecules, for example, solubility, toxicity, bioactivity, etc. So this has become a really dominant application area for graph neural networks. One thing I will mention is that the state-of-the-art techniques in this space, so for example, I'm citing a paper here by Wengong Jin from MIT, they tend to not just use the simplest graph neural networks, they tend to also do more sophisticated graph neural networks that take into account the hierarchical structure of molecules. So there's been a lot of work on adapting graph neural networks to work with the particular properties of molecules, and in particular, molecules are really built from motifs. And so this idea has been leveraged in a lot of recent work. And so a good reference here is what I've referred to as Wang Jin, who has a 2020 paper on hierarchical graph neural nets for molecules. And just as a quick pointer here, there is an open challenge actually, and so there's a number of researchers who've posted their models where they're trying to train graph neural networks to predict the efficacy of drugs actually for treating secondary bacterial infections. So I recommend this both as somewhere which is another data source, but also really as a place for you to go and look and see what are the state-of-the-art techniques that people are using. Most of the techniques that people are using here, they'll actually give the name or provide a link to their code. So that's quite nice. So the related task to trying to predict whether or not a molecule is going to be useful for treating COVID-19, and I should say there's still a lack of data really for that direct prediction task, but the complement to this is not just predicting whether or not a molecule is useful, which might be good for trying to figure out if existing drugs could treat COVID, but the other really big application is actually trying to discover novel molecules that could be useful. Here, there's really two styles of approaches. The first style of approach is what I call this latent state optimization approach. The idea here, again, keeping things pretty high level, and I apologize if there's a little bit of jargon or some details that are not fully fleshed out. But the key idea here is that we're going to learn an autoencoder using graph neural nets or other techniques, where what we do is we train a model that takes the molecule graph structure, embeds that molecule graph into some low-dimensional latent space, and then we train a model that can decode back out the molecule graph structure from this latent space. So what we end up with is a way of representing molecules as points in some usually 100 or so dimensional vector space. We can then train what we call a property prediction model, which tries to figure out which parts of this latent space correspond to molecules with different types of properties. So you might say, oh, this region of the latent space seems to have molecules that all interact with this particular protein that's known to be important for, say, the COVID-19 entry process. And then we can say, okay, I'm going to sample and look around in that region of latent space and decode out molecules that might be good candidates for treating COVID-19. It's a very, very difficult problem in terms of the actual machine learning engineering, but it's a problem that people are definitely making progress on in the last few years. And again, I've given incomplete citations for some of these, but the image I've taken here is from an ACS paper by Gomez-Bombarelli et al., where they really lay out this general paradigm, not just for COVID, but for drug design in general. The other type of approach is what we call a, here it is. The other type of approach is what we call a search or reinforcement learning based approach. So for those of you who are interested in RL-based methods or reinforcement learning and game playing, there's actually a really good use for these kinds of techniques. So for example, pretty similar algorithms to what you would use in the AlphaGo and other techniques that have been used to play board games like Go. And what you do here is you really treat the molecule design problem as a game, where the agent's trying to choose motifs to add to the molecule at each time step. And then the reward is how good is this molecule at, say, binding or docking to different proteins that are known to be relevant for COVID-19. And here I provide a link, again, to actually a web page from my institution, NELA, where we have a large initiative involving around 30 researchers that's actually trying to go about this and build a reinforcement learning agent that uses graph neural networks in order to design de novo molecules for COVID-19. And many of the things we're using there, I hope the website should be up to date now in terms of links to public code and so on. So just to give you a quick sense of the challenges here and talk a little bit about why computational drug design, what we call de novo drug design, is not necessarily the only way that we can try to use these techniques to help, is first off, it just really takes a very long time. So what I'm showing here in the top figure is the typical drug development pipeline, which essentially, first off, you figure out, say, what is the protein or pathway you want to target. Then there's somewhere between 3 and 20 years of trying to figure out what is a small molecule that might work for that. And then you have another, maybe 7 or so years of trying to figure out how to bring this into trials and get it approved. The goal here with using machine learning and reinforcement learning and graph neural nets to help this is really reducing this big finding a promising molecule part of the problem, this lead discovery, as they call it, from something that's more of a decade to something that's maybe half a year. But it's important to note that we still need to do clinical trials. We still have to do a lot of biological assays. So even if we're able to reduce the time it takes to find a promising molecule by an order of magnitude, the hope with these is that we can come up with something that's highly effective in the couple years time frame, but really actually having this make an impact in the immediate future is less realistic just because of the trials that you have to do in terms of making sure it's safe. So the other type of approach that people do, instead of trying to design new drugs, you try to do more what we call treatment design. So here, there's really 2 types of approaches. One is let's try to leverage known structural information about the protein structure and then try to infer from this 3D structure what might be good, say, existing drugs that might attack this protein or bind with this protein. So the methodology for this style, again, here where we're not trying to design a new drug, but just find some treatments that already are out there and approved that could help, is we basically use the same technologies I was talking about in the last few minutes, but we try to apply them on existing drugs rather than generating new drugs. The other type of approach, and what I'll spend the bulk of the remaining time on, is what we call a network-based approach, which is where we're actually trying to leverage the complex heterogeneous network of biological interactions between drugs, diseases, and proteins, and to use all this information to infer what might be useful drugs that we can repurpose or other treatment strategies that we can employ. So again, the idea here is we can really think of the interactions between proteins, the interactions between proteins and diseases, the interactions between drugs and diseases, the polypharmacy side effects or efficacies that you see with drugs in terms of when you take drugs together, what happens. We can think of all of these different biological interactions as being embedded within a large heterogeneous network. And our goal, in some sense, is to infer relationships that we haven't observed yet within this network. So we view this as what we call a relation prediction problem, where we're trying to infer missing relationships. And it's important to note that I'm talking about this in the context of drug repurposing, but this idea of trying to analyze these large heterogeneous networks and predict missing information in them is also analogous for many applications that are relevant to COVID-19. So for example, epidemiological forecasting, trying to look at not just drug repurposing, but trying to understand, for example, what might be other proteins you might want to look into and do more assays on. All these different things can be often represented as network or graph problems. And the key intuition here when it comes to drug repurposing is that we can think of diseases as really being kind of embedded within a subgraph of proteins that they're interacting with within the interactome. And we can think of drugs similarly as being interacting with a subgraph of proteins. So we have this heterogeneous network, and really one of the classic ways that people try to approach computational drug repurposing is trying to find overlaps between these subgraphs within the interactome network. So trying to find drugs and diseases that have an overlapping interaction subgraph within the interactome. Of course, this ignores all kinds of interesting things relating to epigenetics, relating to genetic transcriptions and interaction factors, things like that, which can be added in, but I'm keeping it simple, just talking about the protein interactome here. So just to give a quick couple example of what people have already done in this space, and just as a time check, Daniel, I have 5 minutes. Oh.
Yep, just a few more minutes would be perfect.
Yeah.
Well, thanks.
Yeah. Great. So just to give a really quick overview here. So what people have already done, people have assembled proteins that are likely to interact with SARS-CoV-2 based on other known coronaviruses. This is work by Xu et al. And they identified a number of promising candidates by exactly doing what I just said, which is examining the overlap between the drug subgraph and the COVID-19 inferred disease subgraph. Even slightly more recently, a very nice paper where they actually used affinity purification mass spec to identify the actual proteins that interact with SARS-CoV-2. And again, they then identified what are all of the important subgraphs in the human interactome that interact with COVID, and then tried to recommend some possible repurposing drug candidates based on these interactions. And more recently, there's been a few works that have came out just in the last few weeks of achieving even stronger, more accurate predictions by adding graph neural net technologies on top of this. So just to jump to one thing that I do want to mention is that one of the really exciting things in terms of, well, what can we do that is more interesting than these other papers that are coming out on arXiv every week in this space in terms of computational drug repurposing and other analyses for COVID-19 is also thinking about combinations. So not just thinking about having a drug subgraph that interacts with the disease subgraph, but thinking of having multiple drugs that interact in complementary ways. And then just to close, I want to quickly highlight that I focused here on computational drug design and computational treatment design. That's where I have the most knowledge. But all of these graph neural net, these network analysis type techniques I've been discussing, they're very relevant also for epidemiological forecasting, all these other applications. And again, I explicitly endorse, for example, designing a technique that tries to predict somebody's risk factor for contracting COVID, because there's a lot of ethical and other concerns there, but it definitely is a direction where these sorts of techniques could be useful. So I'll maybe just end there and allow things to continue on time.
Perfect, Will. Thanks so much. We're really honored to have your lecture. So for the participants, we now will move into the next stage of our Complexity Weekend, which will begin in 2 minutes at 10 a.m. And so here I'm going to share my screen so that you can see where you're going to figure out which participant group you're in. So let me just, Will, you can leave the chat. So you should be able to see my window. It looks like you can. We're in the program documents. And then over on the tab participant info in column B, you can see which workshop group you're a part of. And so this is just randomly sorted. And the idea is that you're going to be juxtaposed with just a truly random subset of our awesome attendees. And then in the schedule area on Saturday, you can see which Jitsi link you should join. There's 6 groups, so join into the Jitsi link of your group. And then we're going to have 3 30-minute sessions and then a 15-minute break. And then our last 3 30-minute sessions. So it'll be 3 30-minute sessions in a row, 15-minute break from 11:30 to 11:45, and then we'll do another hour and a half of sessions. And right after that, we'll adjourn to our 45-minute lunch break from 2 p.m. So I'm going to keep this live stream going really just until everybody has quit. So as soon as you've joined into the Jitsi for your group, the facilitator should be in and waiting for you. But I'm going to keep on the live stream now just so that anybody who is having an issue with joining the Jitsi or where the facilitator hasn't yet joined, I'm going to be here with you live, making sure that every person gets into this first Jitsi. Special thanks to Justine and Will, really, for telling us about 2 high-level perspectives on data science and how it's being used in some crucial areas that I know a lot of teams are interested in thinking about as well. And also, thanks a lot for keeping us on schedule. It really makes sure that every facilitator is able to give the full contribution that they signed up for, because there's exactly 30 minutes. So I'm checking back into the chat. and it looks like people are starting to join in. But again, maybe even just to signal that you're ready for your Jitsi workshop to begin, you can just quit this live stream, and I'll be able to see how many people are still in the live stream and use that as a proxy of understanding whether everybody has made it into a live stream. Let's just go over some of the teams also that we have in our main conference. So I'm going to browse all channels and just make sure that I'm joined into every team. And then let's just talk through a few of these channels again while everybody is joining the correct Jitsi link. So here we are, Complex Weekend, May 2020, and look at how many channels we have. We have Ask Facilitators, where people can ask questions about facilitators or the things that they're interested in. We have a Data Support channel, where we'll be able to specifically provide support for you if you have any questions about data. Then we have our Explore channels. So Explore channels are where the discussion can begin around topics. And so this isn't to isolate or to silo discussion. This is to focus people who are focused in a certain area and have conversations that also cross boundaries and bring complexity science into every aspect of the conversation. And the Explore channels that we have are art, bias, cognition, complexity itself, data and ML, machine learning, Explore economics, Explore education, Explore FEP, which is the free energy principle, Explore health, Explore hospitality, Explore logistics, Explore music, privacy, resilience, security, supply chain, and transport. And if you want more Explore teams to be made, we can do that. Then there is the general. And so in general, we're having our main chat. We then have I need a team, where people can post if they need a team. We have introductions, where everybody is providing an introduction. We have random for just any off-topic things you find. Requests, where you can make specific requests that hopefully will resolve as soon as possible. And then a specific tech support channel, where we'll try to resolve any of your tech problems. So let's just make sure that everybody is joining into their Jitsis. So again, you go to participant info, and this workshop group is the letter where your Jitsi group is determined, and then jump into the second sheet, which is the conference schedule. So I'm going to unshare my screen. It looks like the live stream attendance is rapidly dropping off, which is exactly what I like to see. That means people are joining into their teams. So that's great to see. Let's see. Does anyone else have any feedback or any information about the team joining process? How is that going for everyone? While I have a few minutes, I'm going to just go over the rest of the afternoon, just in case somebody has some questions that they want to have addressed right now. So here we are in the conference schedule tab. And let me just double check that everybody is getting onto the teams. Good. So Friday night was great. We had 3 of our facilitation teams, Sean and JP, introduced us to Sean Griffin, Sudebian Prabal, and Michael Zargum. We had a great keynote by Carlos and some fun with Monica last night. We just heard from Justine and Will give their talks. And now we're currently in the middle of this 10 a.m. to 1:15 block. And so this is where you're going to go to your participant info to get your workshop group, and then click into the Jitsi room that you're going to be in a group with. And so once you've done that, you can drop out of the live stream. Then you can just participate with your small group. Then after your last workshop is over at 1:15, you're going to rejoin lunch, just hang out, rejoin Online Town if you'd like. We can jump over there now, actually, see who's out there. And then At 2 p.m., we're going to rejoin with a new YouTube live stream. We're going to hear 3 talks from 3 of our facilitators, Monica, Jason, and Jared. And then from 3:25 to 6 p.m., that's when the real official hackathon is going to begin. At that point, we're going to give you all a Google Forms to fill out if you want to register for a team. What registering for a team will do, when you tell us the Keybase team that you formed and all of the Keybase usernames of the people who are on the team, it'll really help us make sure that our 2 goals are accomplished for the teams. The overall goal of the conference is to learn complexity by doing, by being in the community. But the 2 sub-goals that we really have are to get every individual on a team if they want to be on a team, and not just a team where they're a rider or hanging on, but a team where they're a valuable and contributing member. And secondly, that we can use our facilitators, the time that they've set aside for us, to really catalyze these unique teams in this unique space. So if you're not in a team, let us help you find a team. Once you're on an officially registered team through the Google form, then let us know how we can help you. Let us know how we can offer facilitation or data or any other sort of consultation to make sure that your team is as successful as possible. During the 3:25 to 6 p.m. session, we'll also be in this live stream. So we'll be hanging out and be able to have some conversations. For those who are not in a team yet, we have the channel hashtag I need a team. And so that is always a place where if you need a team or you want another one, you can always come back to. And that will be a channel that's open past this weekend. So for people who are looking for collaborations that maybe just this weekend you're still processing a lot of what complexity means, it's absolutely fine. Take your time with it. Let's join into this room. And we can see that it looks like there are a few people around. We'll let it load up a second. And I'm just going to check to make sure that everybody is getting on to the teams, their Jitsies. So tech support. Looks like people are figuring out tech support. That's really good to see. In Explore Education, we're seeing some really cool lectures that are about the labor market and professional skills and competencies, with a special focus on making sure that the digital divide and that socioeconomic inequities are not exacerbated. Ask the facilitators. People are asking about groups, which groups they're in. So I hope at this time that everybody has found their group. I'm going to just navigate around and see what these people are doing. Yo, Jared, Mariana. All right, so seeing as it's been 10 minutes now into our first session, I hope that you've all found the groups that are relevant. I hope that you've all joined on to your Jitsi group with the facilitator. And the first facilitators who are going to be presenting, in Group A, we have Chen Ling. In Group B is Richard Cordes. Group C, Stephanie Heckman. Group D is Blue Knight. Group E, Rose Sagan, and Group F is Marek Laskowski. So we're not going to worry too much about which facilitators are going to jump into which room. Suffice to say that there's 10 facilitators who are giving workshops this morning. Some will be giving 4, some are going to be giving 3 or 5. We've tried to balance it out so that it's possible for them to give these small group sessions to all of you. Just checking back, we're down to just a few live stream video visitors. So for those of you who are just chilling to listen to this monologue, that's great. However, you can also join these Jitsi teams, because I think that what those facilitators have to say and the ways that you can interact with other attendees are going to be much greater than whatever it is you're doing now if you're still watching this live stream and it's 10 a.m. However, for those who are in different time zones, or for those who this time just didn't work out for, we're going to have more events. We're going to have events at different time zones so that everybody can participate. And we're really testing out this experimental format to understand how we can deal flexibly with different amounts of facilitators that are available and different amounts of attendees that are available. And that's really what's going to allow this format to be something that's used in a global context to bring about complexity thinking across different areas. So for the 10 or 15 of you who are still watching, you really all should be joined into a Jitsi. So I hope that you found it by now. And I'm going to terminate this live stream just to really make it clear that you should be joining into a Jitsi at this point. Please, in the general chat, post anything. If you're having any trouble, just let us know. So I'll talk to you later.